Hi all, welcome to new class. Today's class is about maximum power transfer theorem. So we are discussing about network theorems. So next is maximum power transfer theorem. It states that maximum power is delivered from a source to the load when the load resistance is equal to the source resistance. Or we can say a resistance load being connected to a DC network receives maximum power when the load resistance is equal to the internal resistance or the Thevenin's equivalent resistance of the source network as seen from the load terminals. And this is the case of DC network, and in AC circuit maximum power transfer occurs when the load impedance is equal to the complex conjugate of the source impedance. So this is the maximum power transfer theorem. Let us discuss more about this maximum power transfer theorem. So consider a DC network with a variable resistance RL is connected to the DC network. Then here, after applying Thevenin's theorem, we can draw it like this. That is, this is VOC, then RTH, then RL. So this is the current I. And here, to determine the value of RL for which it receives the maximum power from the DC source, we have to find the value of current I, because power is equal to I square into R. So for that, first of all find the value of current I. So that is equal to VOC divided by total resistance, that is RTH plus RL. Then power delivered to the load is equal to P is equal to I square into RL. Then we have I is VOC square divided by RTH plus RL the whole square into RL. So this is the value of power delivered to the load. Then to determine the value of this RL for maximum power to be transferred to the load, we have to differentiate this power with respect to RL. That is, to get the maximum power delivered to the load, we have to differentiate this power, that is dP divided by dRL is equal to 0. So differentiate power with respect to the unknown value of the resistance, that is RL, and equate to 0 and find the value of RL. So here we get differentiating this one, that is d by dRL of VOC square divided by RTH plus RL whole square into RL. And here this VOC is a constant equal to 0. So we can write VOC square into derivative of this one. So this is applying the quotient rule, that is applying quotient rule. We get numerator denominator into, that is RTH plus RL square into derivative of the numerator, that is derivative of RL with respect to RL is 1, then minus numerator into, that is RL into derivative of the denominator, that is derivative of this one is 2 into RTH plus RL into 1, then divided by denominator square, that is RTH plus RL the whole raised to 4. Now equal to 0. So here it is, there is a square bracket here. So here now we can equate to 0. So VOC square get cancelled, and also this RTH plus RL all raised to 4 also cancelled. Then the remaining thing is the numerator. So we can write RTH plus RL the whole square equal to 2 into RL into RTH plus RL. So 1 RTH plus RL we can cancel. Now we get RTH plus RL is equal to 2RL. So we get RL is equal to RTH. That is, to get the maximum power to be transferred to the load resistance is equal to the source resistance. Now we can find the value of maximum amount of power. To get the maximum amount of power, put the value of RL in this equation. So put the value of RL in this equation, then we get the maximum amount of power, that is P max equal to VOC square into RTH divided by, there is RTH plus RL whole square, that is 2 RTH the whole square. Then here we get 1 RTH is get cancelled, then we will get VOC square divided by 4 RTH. So this is the maximum amount of power. So VOC square divided by 4 RTH, and to deliver the maximum power to the load resistance to be equal to the source resistance. Next is the steps for applying the maximum power transfer theorem. First one is remove the load resistance and find Thevenin's resistance of the source network looking through open circuited load terminals. That we have studied in the Thevenin's theorem. Then second one, as per maximum power transfer, RL is equal to RTH, that is the load resistance is equal to the source resistance. And the third step is find the open circuit voltage across the load terminals, VOC. That we have already studied in the Thevenin's theorem. Then fourth one is maximum power, that is find the maximum power is equal to, that is P max is equal to VOC square divided by 4 RTH. So this is the steps involved while applying the maximum power transfer theorem. Now let us do the problems related to maximum power transfer theorem. Let us do a problem. Find the value of R such that maximum power transfer takes place, and also find the maximum power. So this is the given network and you have to find the value of R. So to apply the maximum power transfer theorem, our first step is find RTH. So to find RTH, we have to deactivate the sources. That is, by using the Thevenin's theorem, we have to deactivate the sources. So this is a current source, so it is open circuited. Then 10 ohm. Then voltage source is short circuited. Then next is 5 ohm. This is 10 ohm. and we have to find the value of RTH by removing the load resistance. So here RTH is equal to 10 ohm and 5 ohm are in parallel. So we get 10 into 5 divided by 10 plus 5, and that is equal to 3.33 ohm. So according to maximum power transfer theorem, RL is equal to RTH, and here it is R. R is equal to 3.33 ohms. So this is the second step. Then third step is find VOC, that is open circuit voltage. So for that, consider this network. So redraw the given network. So this is 5 ampere, then 10 ohm, 20 volt, 5 ohm. Then we have to find the value of VOC. So to find the value of VOC, let us apply the nodal analysis. Let V be the voltage at this node. Then we can write, this is the current source. So 5 is equal to V divided by 5. Then plus, here this is plus 2 minus. So V minus 20 divided by 10. That is equal to V into 1 by 5 plus 1 by 10, then minus 20 by 10 is 2. So we can write V into 15 divided by 50 equal to 7. So we get V is equal to 23.33 volt, and this is the VOC. Now we can find the value of maximum power, that is P max is equal to VOC square divided by 4RTH, and that is equal to VOC is 23.33 square divided by 4 into RTH is 3.33, and that is equal to 40.75 watts. So this is the maximum power delivered to the load. So in this way we are applying the maximum power transfer theorem. Let us do another problem. Find the value of R such that maximum power transfer takes place, and also find the maximum power. So we have to find the value of R. So by applying the maximum power transfer theorem, our first step is to find RTH. So to find RTH, we have to deactivate the sources. So there are two voltage sources, so we have to short circuit it. Then redraw the circuit diagram, and we have to find the value of RTH by removing the load resistor R. So this is 1 ohm, then 2 ohm, 5 ohm, and this is again 1 ohm. So here RTH is equal to, this 1 ohm and 2 ohm are in parallel. So 1 in parallel with 2, which is in series with this 5 ohm resistor. Then again in parallel with this 1 ohm resistor. So we can write 1 into 2 divided by 3 plus 5 in parallel with 1 ohm resistor, that is 2 by 3 is 0.67. So we get 5.67 into 1 divided by 6.67, and that is equal to 0.85 ohm. So this is the value of RTH. Now the next step is to find, so here RTH is 0.85, that means RL is equal to 0.85 ohm, that is equal to R. Then next step is to find VOC. So to find VOC, here we have to remove R and find VOC. So redraw the circuit diagram. So here we have to find the value of VOC. To find the value of VOC, we have to apply KVL in this loop. So VOC, then here we have to find the voltage drop across this 1 ohm resistor. Then only we have to find the value of VOC. So for that, first of all, apply the mesh analysis in the first two loops. Let I1 and I2 be the currents in the two loops. Then applying the mesh analysis by inspection method, we can write here the self resistance is 3 ohm, then mutual resistance is -2. Then in the second loop, self resistance is 8 ohm, and this is -2 into I1, I2 is equal to, in the first loop 4 voltage, second loop 0. Now we have to find the value of I2 to find the voltage drop across this 1 ohm resistance. So for that, I2 is equal to delta 2 divided by delta, and delta 2 is the determinant of the R matrix by changing the second column matrix with column elements with the voltage elements, and delta is determinant of this R matrix. So we will get delta 2 is equal to 8 divided by 20, that is equal to 0.4 amperes. So I2 is equal to 0.4 amperes. Now we can apply KVL in this loop. So applying KVL for this third loop, we will get VOC minus voltage drop in the 1 ohm resistor is 0.4 into 1, that is I2 into 1, minus 6, because this is plus 2 minus, or minus 6 equal to 0. So we will get VOC equal to 6.4 volt. Now we can find the maximum power, that is P max equal to VOC square divided by 4 RTH, and that is equal to VOC is 6.4 square divided by 4 into RTH is 0.85, and we will get the value of maximum power as 12.05 watts. So this is the maximum power delivered to the load when the source resistance is equal to the load resistance. So in this way we are applying the maximum power transfer theorem. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.